Alright guys, I really did not want to do these notes on a video, but I guess we don't really have a choice. So um, yeah, optimization. This is going to be the last section in the chapter 3 that we're going to cover before our test. So yeah, let's just go through this. So first of all, I'm going to pull up my PowerPoint because I want to show you a video. So this is another one of these 3-act math videos. If you remember, we watched one of these before, so I'm going to, let me pull this up here where we can see it. So let me show you this video, and we're going to start with this problem.
So I'm there on the beach with my friend Ben when we notice a taco cart up the road. Ben wants to walk straight over, but I'm thinking we walk a lot slower in the sand than we do on the street. So I say we walk straight to the street and then down the street to the cart. So we went our separate ways.
All right, so again, the question that probably comes to mind is which one of these guys is going to get to the taco cart first? So in order to know that, first of all, we need some information. And here is the information that we need. So go ahead and write this down. Basically, if we're looking at a right triangle here, the left side is 325.6. The distance that they walk on the sidewalk is 562.6 feet. And then here are the rates that they walk in the sand and on the sidewalk. We're assuming that they both walk the same rate in the sand at 2 feet per second. So, all right, let me pull up the board here. All right, so let's go through this. Now, basically what we are looking at here to start it off with is we want to know who's going to get to the taco cart first. So they both start out at the same position. Okay, so they're both starting out down here, and they're ending up over here at the taco cart. So we know that this side over here was that 325.6, and the top part was 562.6. So again, like I said, we know that the rate, let's say the rate in the sand was 2 feet per second. I'm just going to write all this information out here, and I'm just going to call this the walkway. The rate on the walkway was 5 feet per second. Okay, so what we're going to do is, first of all, let's figure out Dan, or I'm sorry, not Dan, Ben. Ben was the guy that did this route that went this way. Okay, so this is Ben went this way, and then the guy that made the video is Dan. So Dan went that way. So for Ben, in order for us to figure out Ben's, first of all, we need the length of this side over here. So do your Pythagorean theorem and see what you get for this side length. They have everything in 1 decimal place, but we'll just go ahead and leave it as 3 decimal places since that's what we're used to. So go ahead and do that, 3 decimal places. All right, so hopefully you paused the video and did that and then come back. So you get 650.026. And what I would suggest you do is just leave that number in your calculator, and we'll just use that to get a little more accurate number. So we're going to take the distance, so the 650 point, again, keep that number in your calculator, 026, whatever it ends up, there's more digits there. Leave them all in your calculator. Feet, we want to figure out how many seconds did this take Ben. So we're going to multiply this by, we know that he traveled 2 feet in 1 second. Okay, so hopefully you remember that, whatever you called that, dimensional analysis, converting units, whatever you called that. So basically we're going to take 650 and divide that by 2, and we get 325.013, and again there's more digits there, seconds. We want to know what is this in minutes and seconds, so we're going to go ahead and Divide that by 60, and then you get approximately 5 point, I have more decimal places written here for this one, 5.416885. So we know that it is 5 seconds, and then when you convert that, I'm sorry, 5 minutes, and then when you convert that decimal 0.41688, blah, 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 when you convert that back into seconds, you end up getting approximately 25 seconds. Okay, so it's going to take Ben about almost 5.5 minutes, 5 minutes, 25 seconds to walk in the sand all the way there. Okay. For Dan, the other guy that walks straight up and then straight over, what we're going to do is we're going to take his distance in the sand, 325.6, and instead of writing it out like we did right here and doing all of this, we know that this is going to be divided by 2 to get his time in the sand, right? Remember, the rate is distance over time is another way to think of that. Or I'm sorry, time is distance over rate. Sorry, I had that backwards. So we're looking for the time. So that's the distance over the rate. And we're going to add to this then 562. He walked 562.6 feet in or on the sidewalk, and there he traveled a rate of 5 feet per second. So when we do this, you can just plug that all in your calculator all at once, and you end up getting 275.32. Okay, that's what I got. Now we can see that he's going to get there first, right? Because this Ben was 325 seconds. He's 275 seconds. So he's about 50 seconds faster. So you could kind of just look at that and say, all right, well, if he's 5 minutes 25, 50 seconds before that would be 4 minutes 35 seconds. But if you didn't, then you could just, like I said, change this to minutes. So divide by 60, you get 4.588, and then it's 6 repeating, which then changed into minutes and seconds, 4 minutes 35 seconds. Okay, so Dan would get there first, even though he traveled a further distance, because his rate on the sidewalk was faster, he could get there faster. Okay, so now let me come back over and see, can you think of any questions that would stem from this? We're dealing with optimization, so if we're thinking in that mindset, what other questions could we come up with here? So let me come over here and I'll show you. Well, first of all, let's verify this. Here's the video of them.
So we went our separate ways.
Of them walking there, so we can see how close our time was to this time. So there we got 4 minutes 35 seconds, 4:34. That's pretty close. And this one we got 5:25. So they have 5:23, roughly 5:23. So we were pretty close with what we got doing that with our math and what they actually got. So here is the follow-up question, and this is what leads into our optimization. Okay, this is going to be a calculator problem. So now Ben has the right idea with, trying to make a straight line to the taco cart, but also keeping in mind that since the rate on the sidewalk is faster, that's a better idea. So the question is, how can we get to the sidewalk instead of going straight up at some kind of an angle over here, so that we're still cutting off some of the distance, but also getting to the sidewalk as fast as possible. So this is kind of the idea that we're thinking, instead of doing that entire route. So we already know that this was faster, not shorter, but faster. So we want to know, is this the fastest? Or if we start to move that corner and we move it over like that, somewhere in here, we will get the best route where we kind of cut off some of the sand but get to the sidewalk as quickly as possible. But the question is, where does that happen? Because we know somewhere out in here it gets closer to Ben's time, which was about 50 seconds longer than Dan's time. So that's the question, and that's really the whole concept of this last section of optimization. So we're going to do this one here quick. So what we want to do is, let me just scroll down and let's look at another scenario here. So let's redraw this triangle. So we know that we have Dan's time was the best, okay? But like I said, it's not. Well, Dan's time was better than Ben's, but it's not the best. So the question is then, where can we kind of cut off this triangle to end up somewhere over here that we can actually get there the fastest? That's the whole concept of the optimization. So again, this side over here is still our 325.6. But then up here, we have to break this up. So we're just going to call this x. And then that means this side over here, let's say if x was 100, then we know that this would be 462.6. So this over here is going to be 462.6 minus whatever that distance there x is. Okay, so we're going to start this off kind of similarly. We're going to look at this right triangle. Let's, you can think of this as some other variable like c or whatever. So what we're going to do is this red distance c is the distance that they were in the sand. So c here is going to be the square root of 325.6 squared plus x squared. Okay, that's the distance. Again, we're looking for time. We're trying to minimize the time. So we will divide this by 2 because that's the rate in the sand. Okay, so this will give us our rate in the sand. Now, we're going to leave it like this because we'll finish this off in the calculator. But we are going to take this value right here and we're going to add to that. I'm going to get rid of the c out front because this is no longer what c is equal to. So overall, the fastest time would be taking that distance or that rate for c and adding to that 562.6 minus x, and this we will divide by 5 because this is his rate on the sidewalk. All right, so we will take this and we're going to take this right here, this function, and we're going to plug this into our calculator. So go ahead and get out your graphing calculator. I'll pull mine up. Try and make this as big as I can so we can see what we're doing here. Okay. So in our Y editor, we're going to type this function in. So hopefully you have that written down. I have it written down so I can see it. But that function right here, both of these, we're going to type that in. All right. So here we go. Square root 325.6. You guys can probably do this a lot faster than I'm doing it right here because it's a little bit more difficult for me to type this in. So over, we're going to divide this by 2, and then plus, let's put the second part in parentheses, so that's all in our numerator. So 562.6 minus x, and that will all be divided by 5. All right, let's graph this and see. I did zoom out, so I knew I would be able to see it in here, but I had to zoom out quite a bit. Okay, if I look at my window, I'll show you this just so you can kind of set your window up the same. So let's change our window. Let's just go ahead and change this. Let's change our window to like negative 600 up to, whoops. Sorry, negative 600. I don't know why it's doing that. Oh, probably because I have a minus instead of a negative. Sorry, there we go. Negative 600 to, let's just change that to 650. Let's go negative, well, the y min, we can actually make that 0 because I can see my graph, it's above that. And then the y max, we'll just make that 900. Let's just do that. And I know that this will show up on there. If it doesn't show up on your screen, when I originally did this, I had to zoom out a bunch of times to get it to show up on the screen. So I did that part beforehand so we could see this. All right, now what we are trying to do is find the minimum. So we can see the minimum is right around here, but we got to figure out what that is. So hopefully you remember how to do that. If not, we hit second, trace, which will get us to our calc. Minimum is 3, so I can hit the number 3. And we got to move over until, we know we're on the left-hand side. So I'm going to just say right there. Move over until I know I'm on the right-hand side. So let's just say right there. Enter. So here we go. There's the minimum. 142. We only care about the x value. 142.1035. So what we would have to do then, let me come back. 142.1035. Is we would come over here and fill in, x. Oh, my board's not writing now. X equals, oh, here we go. X equals 142 point, well, I forget what the number was now. 305 or something. 1035. 1035. Okay, so we could plug that in for the x values. We can plug that number. I'm not going to finish that part out. You guys can finish that. Plug that number in there for your x values, and you will get the minimum time. Okay, so you can plug that in there and get the minimum time. All right, now let's look at a couple. Well, we're going to do one other problem today, and then I'll give you some to try. So we have an open box. Is to be made from a 16-inch by 30-inch piece of cardboard. I'll let you guys write this stuff down. I'm not going to read it to you. Go ahead and do that. So pause the video and write it down and then come back. Okay, so what are we looking at here? Well, we got a 16 by, I can't draw a straight line here. 16 by 30 piece of cardboard. Okay, and also just to kind of explain a little bit here, this is something that companies do when they are, if a company has to create a box to ship their product in or to sell their product on a shelf, they don't want to just be making their boxes using any amount of cardboard. They want to actually do this so that they can minimize the amount of cardboard that's being used to create the maximum volume. So, this is something that is actually applicable in, like an engineering field or something where, you're given the task of, all right, we need to create a box that'll fit these shoes or, this game or, I don't know, any kind of product you can think of that you buy out of a box. Yeah, so this is something that they actually have to do. So now let's look at this. So we're cutting out squares from these corners, right? So each of these corners are going to have squares cut out. So that's where the fold will happen on my dotted line. Solid lines are what is getting cut out. So this is kind of what we are looking at here. Draw my dotted line there, solid line, solid line. Okay, so the solid line, solid red lines there is what, we're going to cut these out, fold up these sides on the dotted lines to form a box, right? So when you are doing, this is a little side note, write this down. When you're doing optimization problems, and we'll talk about this in other notes too, but the more times you hear it, the better you'll be. When we're doing these, you're basically going to have a primary equation. The primary equation will help you to answer the question. Your question here is, what is the largest volume? So our primary equation is going to be the volume equation for in this case, a rectangular prism, which is length times width times height, right? Length times width times height will give you the area of a like a cube or a rectangular prism. So now we need to take some secondary equations and plug them in. So your secondary equations will get plugged in for length, width, and height. Okay, your length, width, and height will have secondary equations that get plugged in. Now, Typically, in most cases, they will all have the same variable. And I'm not going to say they're never going to have the same variable, but I can't think of a case right now that, our idea here is we want to have these in the same variable. There may be some cases where they have multiple variables, but typically there will just be one. So what do we know? Well, the length, let's say this 16 was the length of the overall box. But really, your volume is just this part right here, length and width. And then your height is going to be, this piece right here when this is folded up. Like all of these will be the same because it says they are cut from equal size corners, right? They're squares. Squares, it's important that we know they're squares from each side of those corners. They're getting cut out. So let's throw down a variable. Doesn't matter what we choose. Let's just say x. So that means all of these pieces here are x because we're told that these are all squares that are being cut out, right? We know that they're all squares that are being cut out. So these are all x's. You don't really need to fill them all in here. Just know that they're all x's. So now going back to our primary formula for volume, what is the length? This value right here, what is the length here? Think about it for a second. We know the overall is 16, and we're taking off 2 x's. So 16 minus 2 x's. So what is the width? What is this distance right here? Well, we know the whole thing is 30, and again, we're taking off 2 x's. So 30 minus 2x. And then what is the height? Well, if I take each of these folds here, the dotted lines, and I fold them up, what would be the height of the box? Well, that's x. All right, so let's multiply this out. So you guys go ahead, pause the video, multiply this out, and then see if you have the same thing that I get when I multiplied this out. So go ahead and pause it and do that. So hopefully this is what you got. I'm going to clean that up a little bit. 4x to the third minus 92x squared plus 480x. That's what I got for my volume. So our question now, the question that we have to answer is, how do we obtain the largest volume? So we are looking for a maximum. So this right here tells us that we are looking for a max. How do we find a max? We just did this, so hopefully you remember. How do we find a max? Take the derivative, set it equal to 0, and then find the points where the left-hand side will be a positive, right-hand side is a negative. That gives us a max. Sometimes we only have one point that'll work, but if there are multiple, that's what we were looking for. So let's start it off with our derivative. The derivative of 4x cubed is 12x squared. The derivative of 92x squared is 184x, and the derivative, oops, not equals, sorry. The derivative of 480 is, or 480x is just 480. So we take our derivative and set it equal to 0. Now, I know that these are all divisible by 4, so I'm going to divide them all by 4 before I do this. So 3x squared minus 46x plus 120. And I want to know, first of all, where is this equal to 0? Because if we're trying to find a max or a min, remember the first thing we have to do is find that critical value. We have to find out where it's 0, and then we'll see what the max is. So you have a couple options. You can use completing the square, you can use our quadratic formula, or this actually does factor nicely. So here's another example. I'll show you what I do. I know I showed you this before, but I'll show you it again with another problem here. Multiply your outside. This is the way I do it. I know you guys do like a guess and check or whatever. This is how I do it. Multiply your outside numbers. 3 times 120. Put it up top. So 360. Middle number, negative 46, goes at the bottom. So what I'm looking for is two numbers that will multiply to give me 360 and add to give me negative 46. So think about it for a second. What multiplies to give you 360 and add to give you negative 46? So that's going to be a negative 36 and a negative 10. Right? Negative 10 times negative 36 is a positive 360. Negative 10 plus negative 36 is negative 46, right? So then, the way that we finish this off is we take this number, which is 3, and we divide both of these by 3. And we want to see, does it reduce? 10 over 3 does not reduce. Divide this by 3. Does that reduce? Yeah, negative 12. And I'm going to put it over 1. Okay, so let's come back to our problem here and factor this now. So this factors negative 10 over 3 means 3x minus 10. And negative 12 over 1 means 1x, or just x, minus 12 equals 0. So what makes this 0? Well, x equals 10 thirds, or x equals 12. Now, if we had no context, right, no context clues at all, those would be our two zeros. But let's take a look back up here at the top. If my x is 12, do you notice the problem there? There's no problem with 30, but if x is 12, if this is 12 and this is 12, that's not enough material to get 16, because 12 and 12 is 24. We're over 16, so that's not even an option. So 12, because of the context of this problem, 12 is out. So we actually don't even have to do any work to find out a max. We know that it has to be 10 thirds. Okay? Now, what size should the squares be? That's the question that we're asked there. So the answer is a 10 third. I guess to actually answer it would be a 10 over 3 by 10 over 3 squares. Okay, so that's your length and your width. Or, you know, sometimes they're asked to find what the volume would be or something like that. So this is how we actually do those problems that I referenced yesterday in yesterday's notes. I showed you like a graph or a graphic that had like 5 different open boxes, all that had the same surface area, but all had different volumes. So this is how you actually do that. You could do a guess and check, and then go through it like that. Or, you know, if this is a calculator problem, you can take your volume, 4x cubed minus 92x squared plus 480x, graph it, set it equal, and then find the minimum. Okay, so you have some options there depending on whether it's a calculator or a non-calculator problem. Okay, so hopefully that all makes sense to you, and we will go over more problems. I'll give you another video for tomorrow because I will not be in again tomorrow. I'll give you another video for tomorrow, and then I have no idea what's going on for next week. We'll see what happens. I'll be in touch with you and let you know exactly what is to be expected for next week, but I know I won't be in tomorrow, so I'll give you another video to watch, more examples and more problems to try. So here's some problems for you to try, page 223. I gave you all odd except for number 2, so that you can check your answers. Yeah, I'll give you another video for tomorrow. So if you have any questions on these, just let me know, and maybe I can make a separate video going over each of these so that if you have specific questions on those, you could check. But just let me know. Like if you want me to go over some of these problems, let me know. Hopefully you'll be able to watch the video in 8th period or part of 8th period, and then try some problems in 9th period so that you can ask questions. So just let me know if you have questions then.